Good morning, everyone. Good morning, Kevin. Thank you for joining us for the last day of the Great Salt Lake Issues Forum. We're so happy to have you here. Thank you to all the Friday morning early risers. We have a lot of great talks again today, and then of course the banquet in the evening. So I think let's go ahead and get kicked off. I think we have some really interesting presentations on minerals this morning. So without further ado, I think we can begin our presentations. Thank you again so much for joining us.
So I will echo that thanks to the early risers this morning. Glad to see a few of you are interested in minerals. So I am Andrew Rupke. I am the Industrial Minerals Specialist at the Utah Geological Survey. And what that means is I'm interested in things like construction aggregate or evaporative minerals like salt and potash and gypsum and things like that. That distinction between industrial minerals geologist and a metallic minerals geologist is not completely clear because lithium, for instance, which is a metal, falls under the industrial mineral purview. And that will be relevant to what we chat about this morning. Okay, so I have a short outline for you this morning. And really I want to do two things in this talk. And as I thought about this audience, I thought it might be good to kind of paint a picture of the mineral landscape that we're kind of living in right now. But the next thing I need to do then is tee up Eliot for his talk about lithium. And so to do that, I'll talk about a short study that I did for FFSL a couple years ago, looking at how some of the resources in the lake have changed over time, particularly potassium, magnesium, and lithium. And in regard to the mineral landscape, a lot of the focus will be on critical minerals. I should mention that. Okay, so really quickly, let's look at the operators and producers on the lake, just so you can have that in your mind a little bit. So on the south arm, we have Cargill and Morton Salt producing sodium chloride for various applications. We had US Magnesium. In the past, they had produced magnesium metal. A little bit of lithium and some other byproducts, including sodium chloride, chlorine gas, things like that. But as most of us know, they were idled in late 2024, and now the state owns that operation. And then in the north arm, we have Compass Minerals producing potash, magnesium chloride, and some sodium chloride as well. Okay, which of these minerals are critical? Well, that's what those green arrows are telling you. So potash is considered a critical mineral, also magnesium, metal, and lithium. Okay, you don't need to read that. So these are a couple different definitions of critical minerals. The first one is from the executive order in 2017 that kind of kicked off the current critical mineral push in our country. The second is from the Energy Act of 2020. Again, you don't need to read these. I just put those up there so you could see them. But our working definition of critical mineral this morning will be basically a mineral commodity that's important, and typically the importance is tied to the economy, shocking, or national defense. But that mineral commodity is subject to, or there's potential for supply disruption. Okay, but why do we have this critical mineral list at this point? We're kind of in this critical mineral moment. And so take a look at this chart on your right. And again, you don't need to read the words. You just kind of need to visually take it in. So on the left side there, you have a list of mineral commodities. And then in the center there, you have a chart that is an indication of how much of those mineral commodities we import. And if the line is completely blue, that means we import 100% of that mineral commodity. And so what you need to take in from that graph is that there are a lot of mineral commodities that we are very reliant upon other countries to supply to our country. And so that was kind of the impetus behind the initial critical mineral list. Now, not all those are critical minerals, but that just kind of gives you a picture of the mineral resource world that we're living in. And then I've got a couple of headlines there on the left. Just so that this has practical implication in the real world. So China, for instance, in late 2024, put some export stops on some critical minerals like gallium and germanium. And so this has, again, practical implications for the real world. So they can use that to leverage, as leverage in negotiations and trade negotiations and things like that. So, and as another example, just this month, China put a ban on the export of sulfuric acid. Now, sulfuric acid is not on the critical mineral list, but it's used significantly in the processing of other mineral resources. So it could have some downstream effects, and it's also used in the production of fertilizer. Okay, but the critical mineral space is a dynamic one. The list is not static. It changes over time. So the USGS is the keeper of the critical mineral list, but they are mandated to update that every 3 years. And that's updated based on things that are happening in the market, but it's also updated based on their changing methodology for deciding what is a critical mineral. So the list changes. We've had 3 lists since the 2017 executive order. So one in 2018, another in 2022, and then in 2025 is our most recent one. And so relevant to the lake, potash was on the original 2018 list. It was then removed in 2022, but then the war in Ukraine started. And since Russia and Belarus are major exporters of potash, it was then added back to the list in 2025. Okay, so in the new critical mineral list, we've got 10 new elements that were added to the list. Things like phosphate, copper, which was a big one for Utah particularly. And then just as another example, I've got this note here about sodium batteries. Oh, it looks like I need to hold the mic a little closer here. Okay. So I've heard in the last few months all this buzz about sodium batteries. I have no insight as to whether that will become a reality or not. But it could, and so it could be that in 10, 15 years, we're talking a lot less about lithium than we are now. Whether that will come to fruition, I do not know. But I just want to make clear that this is a dynamic list. Okay, and also in Utah, there is a lot of interest and sort of momentum in the critical mineral space. Just this year, for instance, Governor Cox announced the Mission Critical Initiative. So that is, the goal is to sort of encourage critical mineral extraction and processing in Utah. And there were a couple of bills passed in the legislature related to critical minerals. One that would streamline permitting. It creates a critical mineral council that will look at strategic planning and things like that. It will centralize critical mineral information for the state. So there are all kinds of things going on. And then in April, just as another example of what's happening in the state, the University of Utah announced their Institute for Critical and Strategic Minerals. So there are things happening in the state related to critical minerals. And this map here on the right just shows you some of the more significant critical mineral deposits we have in the state. Okay, a little bit more about what's going on in Utah. So this is a periodic chart, but all the shaded elements there are on the critical mineral list. And so what we try to do at the UGS is kind of update this chart periodically to kind of summarize the status of certain critical mineral elements in the state. The punchline for this slide is just that there's a lot of diversity in Utah related to critical minerals. But what's relevant for the lake? Lithium, magnesium, and potassium in particular. Potentially boron. So boron was a new addition to the list in the last, in late 2025. There is boron in the lake. Whether it would be economic at any point to produce is questionable, but it is present in the lake. Okay, but from a resource standpoint, why are people interested in the lake? And there are some, fairly obvious reasons. There's proximity to infrastructure, for one. There's access to the resource itself. And just to contrast another part of the state, for instance, in the Paradox Basin, there's actually a much larger lithium resource that has higher concentrations of lithium in it. But it's several thousand feet below the surface, making it difficult to extract, difficult to quantify. So in the case of the lake, the resource is just right there and relatively easy to access. Now at the lake, there's the possibility to leverage existing production. So we have these evaporative operators around the lake that can, as they concentrate their product, could potentially produce other byproducts. Okay, but I say those things, but obviously the pressing question is, what does it look like to responsibly extract minerals in a time of water scarcity? And obviously the state is working on that. They've changed some of their rules related to mineral extraction, but that's obviously a question that needs to be answered. Okay, now switching over to the second half of this talk. So a couple years ago, Ben asked me to look at how the lithium, magnesium, and potassium resources may be changing in Great Salt Lake over time. And to do this, we used our brine chemistry database that the UGS has been collecting since around 1966. So we have this large database of brine chemistry data. And I'm going to kind of have to move quickly through this, but we do have a report on our website that you can look at that provides a little more detail on this study. But if you look at the map here, those are the data points that I primarily focused on to look at this as the resource changed. So initially what I wanted to do is just kind of get a sense of lithium concentrations in the lake. And so this graph here is lithium concentration on the y-axis, brine density on the x-axis. And what I want you to notice is, so the blue points are data from the south arm, the red points are data from the north arm. There is a roughly linear relationship with the data in the south arm. There is data scattered there, obviously. That's not surprising with brine data. In the north arm, it's a little more complicated, and this was puzzling initially. So you can kind of see a scatter as you move towards saturation, and saturation is roughly, in this area, when you get around 1.22 to 1.23 in brine density. But then you have this sort of tail on the north arm data that goes sort of below that linear trend as you move below saturation. And just for typical concentrations, you see kind of a wide scatter here, but in the south arm, you typically get between 15 to 30 milligrams per liter lithium, and in the north arm, typically between 45 and 60. Okay, then I plotted up the magnesium data, and you see a similar pattern. So a somewhat linear relationship, but in the north arm, you get this tail again, kind of below saturation. And again, it's this data that I'm talking about in the North Arm. I should mention that our units here have changed. When we're talking about magnesium, it's grams per liter rather than milligrams per liter. Okay, and then you look at potassium and you get sort of a similar pattern. And here we are in grams per liter as well. But then you plot up sodium and chloride and you get this more linear relationship all the way across. Okay, so what's happening here? Well, after I plotted up the sodium and chloride data, I actually started to feel a little bit better about these weird patterns I was seeing in the other data. Because if you think about it, in the North Arm, in the 80s, when we dipped, or the late 80s, maybe early 90s, when we dipped below saturation in the North Arm, what you have is this giant halite crust sitting on the bottom of the lake. And so it's there and readily available to be dissolved and picked up into solution. And so what I think is happening is you're seeing sort of an overrepresentation of sodium and chloride in the North Arm. So you're not getting sort of that typical average sort of chemistry distribution that you would see during normal times. And that's not particularly germane to this conversation, except that it made me feel better about the data that I was seeing. There was some sense to what I was seeing. Okay, but let's talk about actually calculating the resource. So each resource estimate here includes lithium and brine from the north and the south arms. And each point that I selected to do this calculation was a point where we had sampled in the south arm and the north arm temporally close together, so within about a month. And it was a fairly simple calculation, basically taking the concentration and the volumes from that Casey Root put together in 2023, and we used that to estimate the resource. And I should mention, when I'm saying talking about a resource calculation here, these sort of calculations that I did do not meet the requirement of, say, an NI 43101, which is a sort of a standard resource calculation that you do based on the Canadian sort of standards. This is just, a calculation based on the data that we have available. So this does not meet some sort of resource requirement from a legal perspective. Okay, so what you should notice there is we have a big data gap from around the late 90s to the early 2020s. Unfortunately, we did not collect lithium data during that period. So that is a gap in the data. What I do want you to note, so there's some variability before the West Desert project, but then, it's roughly steady if you look at the data from the 90s to what we're kind of seeing currently. There has not been a lot of depletion of lithium. Okay, and I did the same thing for magnesium and potassium. And with this data, and I should actually go back, I do want you to notice that for the lithium resources, is thousands of metric tons, and this is millions of metric tons for potassium and magnesium. I think with the magnesium and potassium, so the similar process to produce this graph here, you kind of see, it's more clear to see that drop during the West Desert pumping project of pumping that resource out into the West Desert. But then again, similar to lithium, you do have sort of a steady resource after that. There is, in 2000, this interesting dip. Oh, if I get my cursor. Around 2000. And I'm not quite sure what to think about that. I've got some ideas about what might be happening there, but I'm not sure that they're good ideas. Okay, and then another part of the study was to think about what the cumulative withdrawal over time is of lithium. And so we calculated that based on known withdrawals, water withdrawals by mineral companies, and then known and estimated lithium concentrations during this period. And our graph here is cumulative lithium withdrawal over time. So I did have to estimate lithium for that period where we don't have data. And so for the south arm, I used that nice linear, roughly linear relationship to estimate that. I used a bit of a different relationship for the north arm, but you tried to use conservative values to estimate that lithium, so I was not overestimating. And what I should note is this estimated lithium withdrawal is not from loss due to production of lithium products. This is loss of lithium from the lake due to production of other mineral commodities. And so an example of that is US Magnesium has been stockpiling lithium as part of their magnesium production process over time. So there is this loss of lithium to the lake. So this loss would include also, for instance, like if there's interstitial brine and evaporation ponds that contains lithium, that still may be available to the system, but is not in the lake brine right now. And so when I ran this calculation, it looks like, you know, there could be up to 200,000 tons of lithium that has been removed from the lake brine. Okay, so we go back to this graph. And so if that's true, if there has been a loss of around 200,000 tons, then we should be down here somewhere with our current lithium resource. But we're not. We've kind of got this more steady looking relationship. So this leads to the question, is lithium recharging in the lake over time? And it would seem to be that maybe it is. And we see similar things with magnesium and potassium. Unfortunately, I did not do the calculation of how much magnesium or potassium loss there may have been over the last several years, but that would be a good calculation to do to see if you know, there's a similar relationship there. So, in the end, it looks like the lake is recharging to some degree in regards to lithium. And I'm going to leave it to Eliot to talk about some of the possibilities there as to how it may be recharging. But maybe I have a couple minutes for questions.
Morning. Can you hear me okay?
Yes.
Good. You mentioned sulfuric acid and how the availability of that from China has been unavailable or reduced. Is that a part of the process for what we're going to be talking about with lithium extraction in the lake? Maybe I should wait until Mark gets up there.
I think so, but I shouldn't answer that question.
Okay.
But for instance, it is, excuse me.
We'll cover it. Okay. All right. To be continued.
It is used down in Lisbon Valley, for instance, to produce copper. So.
Okay. Thank you.
Gonna let me off the hook that easy. All right. Eliot?
I'll let you choose. If you want to turn this one on, it's like that.
Okay, cool. I'll try this one first.
Good morning. My name's Eliot Jagnecki with the Utah Geological Survey. I work with Andrew on the lake, and we are part of the Energy and Minerals program at UGS. I'm not an industrial mineral geologist. I'm a sedimentologist geochemist, and I do love lacustrine deposits. So what I'm going to do today is kind of talk you through some of the lithium processes that might be going on around the lake and how this is potentially being recharged into the lake system. Closer? Does this help? Or is this better? Okay. Okay, so why is lithium important? I think we all know that answer. It helps improve battery life. It supports our EV systems. It's in electronics, industrial applications. Typically, it's been mined from hydrothermal deposits. These are pegmatites, metamorphics, where you have really high grade of lithium concentration, but it comes with costs, right? You have to crush rock. Whereas lithium extraction technology from saline brines and sedimentary basins, it's lower grade, but it's at a larger resource area and at slightly lower cost. So that's why everybody's interested in these sedimentary basins. And these include modern saline lakes around the world, but they're sensitive systems. And they're part of this market, and it's kind of hard to assess their resource viability. Because of that, Great Salt Lake of interest has been, like Andrew said, at a pretty steady state of lithium resources, but what is replenishing the system? Why aren't we being depleted in it? So this study that we did, we were looking at all these proximal sources around the lake, which include playa settings. These are springs, these are the sediments on the playas, these are clays, carbonates, evaporites, just to get a sense of where is lithium retained surrounding the lake, how can it be recycled into the lake, and why do we see this constant steady state. So this is a conceptual model that authors from USGS have put out, and it kind of paints a nice picture of these settings of where lithium is found in these types of sedimentary systems. We have deep sedimentary basins. This would be like your Paradox Formation down in Utah, where you have buried evaporites that form during evaporation of seawater, but they're very far down in the subsurface, so we have to solution mine that brine up to the surface. We have hydrothermal areas where solely the lithium is just being brought up to the surface in little ponds or lakes or springs from hydrothermal or magmatic processes deep down near the crust. But then we have this kind of overlap or not so much overlap of systems where you could have a saline lake surrounded by mountains or a playa lake or ephemeral saline lake that has high evaporation rates. And you can also have volcanism associated with the release of volcanic ash, which turns into clay, blankets these low-lying basins, and then lithium can be as a secondary fractionated product in those clays. And so people in Clayton Valley are looking at these ashes and clays where lithium is hosted in clay minerals, but it can also be in carbonates. So where does Great Salt Lake fall? And I have a hunch, we don't really know, but maybe over in this realm of a conceptual model. So as Andrew was pointing out, North Arm has about 45 to 65 milligrams per liter of lithium, much higher than the South Arm. And what he pointed to on this chart was that tail end of scatter of data. And then as you increase brine salinity, you get much more scatter. And that, like he said, is just sometimes an issue with error in the measurement of brines. So there have been other studies dealing with investigating lithium around the lake. A lot of this has to do with rivers and upstream tributaries where people have measured the concentration from those source points, and they're pretty low. It's 0.001 to 0.77 milligrams of per liter of lithium. Kevin Perry, he measured a bunch of sediment for his dust study, and lithium was part of his analysis, which is a great data set, and we utilized that. That was amazing. And those values are in ppm, which is semi-equivalent to milligrams per liter, but in solids. And from the playa setting, those vary substantially from almost 60 to almost 470 parts per million. Groundwater and spring point sources, they have variable concentrations, again, very low to almost 50 milligrams per liter. And so yet we go back to the lake, which has their steady state of concentration that we've seen through time, which vary a little bit. And so why are these sources connected to the terminal system itself over time? How long does that take? It takes a long time, probably. Or it could be pretty quick near the lake. We don't really know those answers. So what we really wanted to do is get a handle on why this recharge is happening. And so recent studies actually that have shown groundwater being a more substantial contributor to inflow of the lake in the past decade or 5 years. It's around 10 to 12% of groundwater inflow. So lithium is just living freely with these groundwaters, and it's passive and just kind of taking a route into the lake. So with that, and with volumes of the lake, concentration of what we know from rivers, and some of these springs, you can kind of get an idea that the residence time of lithium in the lake in the north arm is about 1,500 years. In the south arm, it's around 650. But that's a calculation just based on these rivers and point source springs. It does not account for localized playa groundwater, which is the groundwater table, or springs emanating from the surface, or the clays that are associated within the playas, or chemical sediments. So what we wanted to do is kind of dig a little deeper in this, utilize Kevin's data set on the playa from all of his dust samples, utilize all the groundwater studies that have reported concentrations of lithium, but then go a little deeper into unique settings, such as large springs that have shown themselves to exist now because of lower lake level, that we can actually physically walk out to. They're far away, but you can go and visit these settings, and they're very unique, and they have variable concentrations of lithium. We can put piezometers in the ground, measure the groundwater level depth, and take samples from the groundwater table. What Kevin did was measure all of the soils exposed on the surface that can produce dust. We wanted to go a little deeper and get sediment that's interacting with the groundwater table itself, so saturated sediments. And those were primarily clays. We also looked at ooids, which are volumetrically abundant all over the lake, and measured lithium from those. And those are actually relatively high in ppm of lithium. We're talking about 20 to 30 ppm of lithium just trapped inside these aragonitic ooids. And then we have old microbialites. These could be Holocene in age, but they have a pretty decent amount of lithium in them. And when you go visit these microbialites, they are completely tattered from aeolian processes, and they're broken up in places, and they're all getting recycled and reworked, brought back into the lake. We also have a basaltic core taken from Rosal West area when Amoco was up there trying to explore for oil, heavy oil. And in these cores, there are vugs and fractures filled with carbonate cement. And those are relatively high in lithium. So when we're putting all the sediments together and plotting it up, we do see a trend here. All of our data are these different shapes and colors down here. At the apex right here, these are evaporites. They're relatively low in lithium, minus some of the cryogenic minerals of mirabolite. Sometimes they can be elevated in lithium because they form around sulfate-rich spring deposits, so they form from enriched brines. Here are the ooids in orange. We have microbialites that kind of bracket the ooids, so we are thinking that they're all probably time equivalent of a different lake phase during the Holocene, when the lake was probably relatively shallow and saline, and when these carbonates were precipitating. So different time sequence, different geologic time processes of how lithium can come into the basin. And then you look at the clays that are in triangles. If I can get my cursor. They're a little lower than Kevin Perry's dust samples. And that's probably reflective of that they are sediments that are supersaturated in a groundwater table. His samples are exposed at the surface. They can become more concentrated in brines through evaporation. And so basically they create the crust that he talks about is basically an effervescent crust of halite or gypsum. And through capillary pressure and wicking at the surface, you concentrate that groundwater that's coming up and making it more concentrated in lithium. And then one data point that he measured was over here, near Morton's outflow from their plant. And we're talking about 465 milligrams per liter. That's a lot of lithium, just in that one location. But from the distribution, by far and large, you can see that the playa is just loaded with lithium. If we look at the seasonal dynamics in the North Arm, this chart is basically showing concentration in black of lithium, density in blue, and temperature in gray. So winter, summer, winter, summer. We can see that during summer, our enrichment of lithium is higher. During the winter, it goes down, and that's because we precipitate mirabolite. It forms on these shores. It forms in the lake. It gets washed onto the shore. It fractionates some of that lithium out and accumulates. But then, when it warms up, it dissolves. Lithium recycles back into the system. That is our Lego guy. He's our geologic scale that sometimes people bring out in the field. He's 5 inches tall. So these mirabolite beach bars can get up to like 3 feet of thickness. So in the South Arm, we have sulfate-rich brine pools. During the summer, they look like this. They're pretty big. They can be a meter to almost 3 meters wide at times. They can be very deep because they're like a sinkhole. And in the winter, because they're so sulfate-rich and the brine is more concentrated than the South Arm, they do precipitate mirabolite again. But what's interesting is that the concentration in the brine pools is approaching 50 milligrams per liter. And the precipitation of the minerals do not retain as much lithium as what happens in the North Arm. I don't know why. That's some other type of precipitation fractionation process. And these things are present all over the place. Dr. Thorne from the University of Utah did a lot of ERT or resistivity measurements around the playa of Saltaire. And it's just cool that he could confirm that there is buried mirabolite in the subsurface, and we have these conduits where groundwater is seeping up to the surface, and that's what we can observe at the surface. So more lithium below our feet in these chemical sediments. When we look at groundwater, I like plotting a ternary, not the Piper plot, because it makes me look at it a little easier. So we simplify it with calcium, alkalinity, and sulfate. When we look at the groundwater, a lot of them are plotting in these calcium chloride fields and calcium sulfate field. And so here's all of our groundwater measurements. This is including Bunce's work that she just published a couple years ago. And essentially the Great Salt Lake brine is down here at this apex, sulfate rich. And so a lot of these groundwaters evolve through evaporation and mixing with rivers, which are not at all in these fields. They're in a sodium carbonate sulfate field. But when you mix them together, eventually they evolve into a Great Salt Lake brine. So just to get your cued in, a lot of these brines are chloride rich, but they vary with sulfate and calcium. So they're pretty salty, all these groundwaters. And then when we plot those against magnesium, sorry, I forgot. Magnesium is kind of a proxy for clays. And so for the sediment, we were cross-plotting it with magnesium because we didn't have anything other than that to cross-plot to make a relationship initially. And magnesium clays, you can substitute lithium in those clay structures. Same thing for groundwaters, they might be interacting with clay minerals. So what we think is going on in these ply groundwaters is that, yeah, you are doing cation exchange with the clays, with the brines, and lithium is just kind of floating back and forth passively under certain conditions and being released and then recycled back into the lake. So here's an example of that spring again. This is the Blue Lagoon. It's a calcium chloride type. It's pretty saline. It's up near Spring Bay. Here's a couple other examples of these springs. They're pretty prominent all over the place. You just have to go looking for them. And they vary in size and discharge and concentrations of lithium. So then, when some of them that are flowing, you can actually measure their discharge, which is cool, because then you can come up with a rate if you know their concentration of lithium. And then you can start figuring out how much lithium from these springs collectively are bringing lithium into the system. The majority of them, here's TDS against lithium, the saltier they are, the more lithium is concentrated in those groundwater brines. And so we were able to measure 28 groundwaters and springs that had flow. And so the flow, one of the max flows was up to 23 CFS, which is pretty high. And there could be more of these springs all over the place. Some could be subaqueously in the lake itself, held back by the lake head, so not necessarily flowing, but just percolating or seeping into the lake itself. And the groundwater on the playas, we don't know what those flows are, but they are flowing. The groundwater is flowing down gradient, but we don't know what that seepage rate is. We don't know what that areal extent is. We don't know what the lithologic heterogeneity is. So there could be baffles or barriers of flow, but the transmissivity in general, all this is flowing to the lake. So with groundwater that was measured with discharge, 28, you can come up with some rate of how many tons of lithium is coming in the lake every year. And so 47.5 metric tons of lithium just from 28 spring deposits. So going back to a conceptual idea of what our basin looks like, we have old volcanics, and again, Lake Bonneville, during that time, there was volcanism. There were ash deposits that covered most of the Great Basin. There are volcanics in the southern Utah that were active. All that could have been flushed into Great Salt Lake. But today, we have hydrothermal activity. We have a geothermal prospect within Great Salt Lake Basin. We have hot crustal rock below our feet, about 10,000 feet down or more. That's circulating with other fluids, groundwater, stuff that's coming off the mountain block. All being convectively driven, coming up in various places. We have hot springs. So we have all these sources. It's very complicated. And we have a lot of clay minerals. So a lot is going on. A lot of geologic, hydrogeologic processes are going on in the lake. We don't have a definitive answer of where the exact lithium is coming from, but it's complicated and it seems to be recharging itself. And so these are just the key takeaways, basically everything I already said. And to go back to what Andrew was talking about, the steady state of the lithium resource, based on this study, which incorporated 2024 to 2025 of lithium in the system, it still hasn't changed. So it seems that the playa system, the ups and downs of lake level, the recycling of the sediments, the discharge of the groundwaters, it's all rejuvenating the system over time. But that time could be short, could be really long. We don't know. And with that, I'll leave you with questions. We did come out with a report. For more information, you can click on the link. And here's some references for when the PowerPoint is uploaded. People can go back and backtrack all the science that's been going on. Thanks. No questions. One question.
Thank you for that. I just have a quick question. I was wondering if you know the time frame, like how long does it take for a mirabolite to form, like from the brine pool into a mirabolite?
The crystallization is quick,
Really quick?
like hours.
Wow.
If it's cold enough. It's a cold brine. If the brine is cold, below 10 degrees C to 5 degrees C, so below freezing, it can form in hours. We've done this in the lab. We put it in a freezer and it instantly comes out within hours. So
Wow, thank
it's
you.
very sensitive and it dissolves quickly.
Hi. It seems like in the water management space, there's a lot of overlooking of groundwater contributions to the lake and having that be modeled in water management plans, but there's research that's happening here in the mineral industry about groundwater and its contributions to the lake. Could you maybe just speak to if there's any collaboration there to help further understanding or potential for collaboration that would help have a more holistic understanding of the water system, especially with climate change being an issue? Groundwater recharge is a huge point of discussion, and so it should be considered for modeling plans.
Yeah, I think it's in the headline media right now. We have a cavern of groundwater beneath our feet, right? Not painted in that exact picture, but it's ongoing. A lot of people are looking at groundwater and studying it. There's people up at the U that are involved with the near shores near Antelope. We've done our own investigations. There's all these investigations that have kind of been isolated little spots or regional spots, but collectively all that data has not been synthesized holistically, so water, how to say it, collectively so everybody has the same picture. And I think that's important and something that needs to be done. Kevin.
Yeah, the northern part of the lake has significant salt, deposition, underneath the lake bed and then on the surroundings. Is there a lot of lithium in that, or is it mostly halite, or what do we know about that?
So we measured halite. We measured the gypsum that forms in the playa. That's relatively low in lithium. Like virtually, there's no lithium in the matrix of those crystals. Could be in the fluid inclusions, that's trapped bubbles of water in the matrix of the crystal. It could be in there, but it doesn't seem to have a major impact on lithium recycling. Okay, I'm out of time.
Good morning. Good morning. Well, I was here just to say, yeah, let's talk about lithium. But we've already had 2 speakers already talking about lithium. So let's really do a bit of a deep dive on lithium. So I'm going to be talking about lithium, Lilac, in the Great Salt Lake. So I work for Lilac Solutions. I'm based here in Utah, along with my colleague Steve Murray. And the picture on the slide here is a pilot plant we operated here at the Great Salt Lake on the North Arm last year. So we'll do a bit of a deep dive on some of the results coming out of that pilot and talk a little bit about next steps in the project and what our non-consumptive technology does. So let's just start for those that have not heard of Lilac Solutions. The other name you may have heard of is Waterleaf. Waterleaf is the project company. It's a 100% subsidiary of Lilac. Waterleaf is the project company that is developing the project here at the Great Salt Lake. So all of our permitting, for those who have seen all our permit applications, has been done through Waterleaf. Lilac has been around for 10 years. So we are primarily a lithium extraction technology company. We have developed an ion exchange media that is very selective in terms of extracting lithium out of brines, waters, very selectively in a non-consumptive manner. You can see from the investors in the bottom right, we have a mix of investors from automakers to battery manufacturers to traditional investors like T. Rowe. And Breakthrough is one of Bill Gates' energy funds. So a really good mix of investors. Okay, so let's zoom out a little bit and talk a little bit about the lithium industry globally in terms of the growth and why lithium is such a hot topic in discussions these days. You can see just from these numbers here, about 1 million tons of lithium is produced annually, and that is forecast to triple in the next 5 to 6 years. It is already like 10-folded over the past 10 years, so it's got a really high growth rate. What is driving this? Primarily the EV market, but also battery storage, and we've seen a lot of like AI. Yes, you need lithium going into batteries to support all of this. And let's come back to now the US. The US only produces 5,000 tons per annum. One facility in Nevada, a facility called Silver Peak. That's about 2% of global lithium demand. So yeah, we don't produce much in the US. We need to bring some of that lithium production back to the US. The projects we're developing here would double that, and it takes us up to 4,000. So there are a number of other lithium projects being developed here in the US as well. I think Andrew already had some of these captions. There's a lot of discussion around critical minerals. Lithium is part of that critical minerals basket. Most of the time when people hear critical minerals, they think rare earth metals, but lithium is very much a part of that basket. And what has the lithium price been doing? Well, it's been pretty flat for some years. Yeah, back in 2022, 2023, the lithium price was up at 80,000, and then it's nosedived to about 10,000. It is coming up nicely right now. It's at about 27,000. I looked this morning. All the analysts are saying it should settle somewhere between 20 and 30,000, and that's deemed a good, sustainable pricing level for lithium out in the industry. Yeah, so how do we pull this all together? Well, using the Lilac technology, we have a fast, affordable, clean lithium extraction technology using ion exchange. And over the past 10 years, we have been developing this technology. You know, ion exchange has actually been around for many decades, primarily used in other industries. We just have tailored an ion exchange media to be super selective to lithium. You can see here we have tested a variety of different brines from all over the world and operated 6 pilots, 2 demonstration facilities down in Argentina, and we are developing our Great Salt Lake project. That'll be the first commercial size facility. There are a number of other clients we are talking to right now in terms of developing additional commercial facilities. So what does that mean for us here in the US? So Lilac is an Oakland, California headquartered company. We produce our ion exchange media in Nevada, in Fernley. And we have an office here in Sandy, just near the soccer stadium, developing the project here in our backyard in Utah. Okay, here's a picture of the facility we have in Fernley. We've just recently constructed and built and commissioned a larger manufacturing facility there. And that facility will be able to produce media that will support 100,000 tons per annum of lithium production, with room in that massive facility to expand further in the future. Okay, so let's come back to the project here at the Great Salt Lake. I love this picture. I think we all love seeing salts crash out, mirabilites, halites. Okay, where's the project located? It's located on the north arm. Why? Well, lithium concentration is higher, so it's more economic to extract lithium from the north arm. It's approximately 2 hours drive from where we're standing here today. You go up past Brigham City, take the highway off near Corinne, and you just head due west. It's a few miles north of Spiral Jetty for those that have been to Spiral Jetty. Yeah, so let's zoom in now to where our site is. I love this picture, nice little drone overhead. This was before we built our pilot facility out there. It's on private land. We have a 40-year lease agreement with the landowner there. It's Steve's truck over there while we were surveying the site. And we then built our pilot facility out there. We designed and fabricated our pilot facility in Oakland in 8 shipping containers, which you then place on site and connect up with piping. Off to the right, we had an office facility and on-site laboratory. We had on-site power generation. We had on-site Starlink, because there's no cell phone reception out there. And the 2 tanks you see on the left-hand side are frac tanks for brine coming in from the lake. So you can see the piping in the distance there. So we've got a couple of pipes out there touching the lake, one bringing the water in to one of the blue frac tanks, and another pipe that sends the water back out. So we needed to go through the right permitting steps to get this built. We worked very closely with the regulators, and all of the information coming out of this pilot facility has fed into the permitting process for our future facility. Yeah, that's Carl Watson, one of our field operations managers during construction, getting one of the intake pipes out into the lake during construction period. And a few more pictures from the pilot plant. So on the top left, you've got the lithium brine frac tank. You can see the pipe going back out, delivering a couple of totes for reagents. Carl there just installing some controls wiring. And on the bottom right, you've got the intake pump. So pretty small intake pump for the pilot. The commercial facility will obviously have a bigger pump, also based on the shore. Okay, we all know the Great Salt Lake brine's tough. I quite like this because this compares the Great Salt Lake brine to other brines that we've worked on down in the Atacama or Smackover here in the US. Super low lithium concentrations at 70. Yeah, in the Atacama, for example, that's about 2,000. That's one of the richest lithium resources down there in South America. But a lot of magnesium. So that's the impurity that we deal with the most. We have a high selectivity in terms of magnesium rejection when we do our process. More pictures of salt. And we have a picture on the right-hand side. We use filter presses in part of our process, standard equipment in terms of what we're doing there. It's really used to maximize water recovery in the process. Okay, we got a tour happening on the top left there, inside one of those shipping containers. Bottom left, we've got that blue tank there on the right-hand side is what's called a multimedia sand filtration unit. We use that as part of our incoming brine filtration step. And on the far right, you've got final products, lithium carbonate product that we produced, unmilled. Once you mill it down, it looks like baking soda. Okay, here's a picture from one of the tours. We had a number of people come out to have a look at our pilot facility. This particular one, we had a group of different regulators come to site, toured them around so they could see firsthand what we're doing during operations. Okay, so a summary of the pilot. Constructed, built, operated last year. So we operated from January through to August. All the samples that we took coming out of here went to state certified laboratory, and those results then fed into the permitting process. So we proved our technology there. We used that information for engineering of our large scale facility. All this info has gone into the permitting steps, and the Eliot stream coming out of here we then used to produce that final product, lithium carbonate, and used that powder to send to a variety of different off-takers, which we've since then we've signed an off-take agreement with a company called Traxys for 10 years, so a very good step on that front. All right, what does our flow sheet look like for the big commercial facility? We'll start on the top left there. So we have our brine intake system pumping water out of the lake. It goes through a brine filtration step. Primarily to remove solids because there is sediment and sand that comes in with the water. That filtered brine goes into box 3, which is where the Lilac technology sits, that ion exchange. There, the lithium is selectively extracted and goes down the page to our Eliot processing step. And there, that's a traditional flow sheet that you'll see in other lithium facilities. So we have an Eliot neutralization step, really to extract any leftover magnesium and calcium. And then you do mechanical evaporation in box number 6, and the water from there gets recycled in the process. Crystallize that lithium carbonate out of the solution, and then you dry and bag the final product. Going back to box number 4, the brine that comes into a process after lithium's extracted, we call that depleted brine or delithiated brine. So you've removed the lithium, and that resultant stream then goes through another filtration step before it goes back out to the lake. Okay, so let's do a quick deep dive on that ion exchange process. It's done in what's called cycles, which are about 3 hours long, and it's broken up into 4 different steps. So the first step, you've got the ion exchange sitting in your vessel. You pump the brine through that vessel, and you do an intercalation step where the lithium gets exchanged out of solution into that ion exchange media. You carry on doing that until the bed is fully loaded with lithium. You then stop that. You move to a water wash step, and that's really to purge the vessel of brine before you move to the third step, where you put a dilute acid stream through there, either sulfuric acid or hydrochloric. We use sulfuric acid for this project, and that does the reverse step. So your sulfuric acid is exchanging with the lithium. So your lithium then comes out of the bead as a lithium sulfate molecule. And once you've finished doing the elution step, you then do another wash water step, and that's to purge the vessel again of that dilute acid before you go back to the beginning, restart the cycle. So part of the reason you do all these wash water steps is to keep these loading and stripping steps separated, and to separate the cycles from each other and prevent any acids contamination going back out with the depleted brine. Okay, so let's do a bit of a deep dive here on the results coming out of the pilot. I'm not going to read all of that, but we didn't just measure lithium. While we did all of this, we measured all the constituents. So you can see 43 parameters, plus flow rates, plus temperature, and a variety of other variables. This was done in conjunction with the states. We had third-party people coming in, taking samples, third-party analysis done at the lab, and all that information was shared on a weekly and monthly basis. Okay, these are some of the salinity parameters. The solid lines are the results from the incoming brine, and the dashed results are the streams going back out to the lake. And you can see across the board, the stream going back out to the lake follows what's coming in, which is what we are expecting. Just want to point out sulfate. We've had a number of questions of, well, does the acids go back into the depleted brine, back out to the lake? No, it doesn't. You can see from the sulfate graph there, sulfate levels are the same. Let's have a look at some of the metal parameters. You see the same trends. The outfalls results match the incoming. So once again, no impact there. The bottom right graph, you can see the iron graph over there. We had a little spike at the beginning of the pilot campaign, and we scratching our heads a little bit, like why is there a bit of an iron spike? Did a bit of a walkabout around the pilot and found those blue frac tanks I pointed out earlier. We had a bit of rust in the frac tanks from, we'd leased the frac tanks, so we did a bit of a clean out, swapped the one frac tank out that was quite rusted, and iron levels came back down to where you would expect them to be. That was a learning lesson for the next pilot. No steel frac tanks. We'll go for plastic tanks instead. Okay, some more graphs over here. Lithium one, as you can see, that's what you expect there. We want to see that delta because we're pulling the lithium out of the water. You can see towards the back half there, a nice broad spread there between intake and outfall. Can show you some of the results coming up of what that means in terms of lithium recovery, but that's exactly what you want to see. And then field parameters here. So some of these parameters you have to measure very strictly within a certain number of hours after taking samples by protocol. Dissolved oxygen temperature and pH. You can see that the pH follows. It's about 7.5 pH coming in from the lake, and roughly 7.5 going back out. So that met the discharge permit requirements of 6.5 to 9. So we keep well within that band. And the temperature graph, you can see we operated here from winter period in January through to August in summertime. Okay, just due to time, I'm not going to spend too much time going through results, but we also did a biologist study with Dr. Bonnie Baxter, and she did 3 sampling campaigns at different periods, and really just showed, the findings coming out of that is our process does not adversely affect the biota, which is also what we want to see. She also did the inoculation experiments, and you can see from the graphs on the right-hand side, they follow the curves that you want. So no adverse effects on the biota as well. Okay. These are some of the results, lithium recovery results. We achieved 87% during pilot campaign, greater than the target 84%. And you can see on the bottom left a very high upgrade of lithium going into the Eliot, and a high rejection ratio of the impurity levels as well. Lithium carbonate production, we produce 99.8% purity, so very, very high battery grade product. And we did a dispersion model as well. So we did the dispersion model over 20 years, 3 different scenarios in terms of lake level. Lake level declining, lake level staying constant, and lake level from the strike team kind of going up a little bit as well. The findings from that are, depending on what the lake levels are, our concentration at during pilot phase was 67 milligram per liter. But if you've got a lake level going down or up, that concentration level obviously changes. We did all of that to really inform over a 20-year time period what does this look like in the North Arm. So this is one of the scenarios where the lake level stays constant or slightly declining, and you can see over here, that's approximately where our facility is. We've got different intake and outfall location points. Very much the objective of this study was to make sure that the outfall wasn't diluting the intake system coming into our plant. So a very, very good outcome for us there. So our commercial facility will be 5,000 tons per annum. And that's a rendering of what it'll look like. We'll be at the same location where the pilot plant was, with pipes touching the lake. So everything above ground. We advance our engineering. So here's a nice little snapshot of the 3D model that we're using during our engineering phase. It kind of matches that rendering. We are currently busy with all the permitting steps. So you can see from this slide there's about 19 large permits we're working on. We've got about half of them. We're expecting to conclude and receive the permits for the balance of the bottom half within the next few months. So things are progressing well on the permitting front. Good collaboration, good interactions with all the different agencies here in state level, county level, federal level, all the different levels of the states. Okay, so what's our execution timeline look like? It's about a 20-month from start to mechanical completion timeline. Looking to break ground Q3 this year once we get all our permits in place. Next steps going forward for our project. We've completed our pilot plant. We've got our 10-year offtake agreements in place. We finished our FEL3 engineering, and we're now busy with permitting steps, completing our balance of project financing for the project, and looking to start construction this year and commission in 2028. Okay, I'll open up for any questions.
Hi, really interesting talk. I had just a couple questions. The wash water volume per volume of brine processed, what's that ratio?
Okay, so the ratio of groundwater or fresh water to brine incoming water is between 0.5 and 1%, so very low. We've got a lot of recycle steps. That flow sheet I showed you earlier doesn't show you all the recycles, so we use reverse osmosis as a technology to recover and recycle and reuse water.
Okay.
So the wash water coming out of those steps goes to an RO system, and we recycle that back. So you've kind of got a bit of a closed loop there for wash water.
Okay. And then you also showed you're removing a fair amount of arsenic.
Yes.
Where's that going?
So small amount of arsenic coming in, a small amount being recovered in that Eliot neutralization step. Some of that is coming out of solution with the calcium and magnesium that is coming out of solution as well.
And so where does that end up?
The solids, the waste, they'll become waste solids and they'll end up going to the local landfill. So we've been working closely with the local landfill there. The arsenic levels are tiny in comparison to the rest of the solids coming out of solution there.
Sure, understood, as is always the case.
Yeah.
And then the media, the spent media, what's the flux of the spent media from the system?
Okay, so the approximate lifespan for our media is about 2 years. Once it gets spent, and spent is not fully spent, it's just down to a certain economic level, we will recover that media, send it back to Fernie, where we manufacture our media and recycle it and reuse it.
Okay, thank you.
Yeah, so one thing confused me about the presentation. It looked like the overall recovery rate was like 87% for lithium, but one of the figures showed the inflow versus the outflow for lithium, and it didn't look like 87%, and it was higher at the end and lower at the beginning, and I was just a little confused.
Yeah, I should have pointed out that's 87% just around our direct lithium extraction box. There is a bit of a recovery loss downstream of that, about 4 points. The graph that we showed there, the beginning months were ramp up, optimization, and once we dialed everything in properly, that's why the gap was so big for the back half. That's where we normally expect things to operate.
And so it's not like a seasonal efficiency change or anything like that?
No, just
Okay.
purely optimization and ramp up.
Thanks for your talk. So if I remember correctly, most of the withdrawal that you took was sort of during winter, spring. Halite saturation really starts to hit sort of in late July, August, September. Do you anticipate sort of differences in efficiencies when the brine is more dense and prone to halite saturation?
Good question. So we operated from January through to August. So during the winter periods, we saw mirabolites coming out of the solution. During the summer periods, that's kind of July, August, we actually had halites coming out of the solution. Interestingly enough, really going from day shift to night shift. So we're running 24/7, but just the few percentage drop in temperature, if you look at the phase diagram, that's what was causing the halites to come out of the solution. So we're dealing with that, poor night shifts guys were dealing with some of that coming out. So yes, there's a salt management thing that you need to design into the facility as well.
All right, thanks.
I was just wondering, how big are your evaporation ponds for the commercial scale?
So there's two what we call surge ponds. They're about 5 hours residence time. And that really is surge to disconnect the pumping system from the lake and the facility.
Oh, okay.
But it's such a long pipe. It's about a mile long. So you need some surge capacity there so you don't have flow rates just going up and down coming into the facility.
Gotcha. I thought what I saw in the flow diagram for the commercial scale outline, you had evaporation concentration as one of your boxes. On the Eliot, yeah. So not a
So you go from
pond.
about, while we're using mechanical evaporation, reverse osmosis only gets you up to about 5,000 milligram per liter. And that's as far as the technology can take you. The mechanical evaporation takes you up to 11,000 for crystallization purposes. But 100% of that, because it's a mechanical evaporation step, you produce condensates, and that condensate's recycled back as water within the system.
Okay, I think I got you. Thanks.
In the effluent, with the metal tests were really great to see. Did you happen to do any organic tests to look for things like phthalates or other plasticizers or other potentially organic contaminants from the process?
No, we tested things like BOD, but the ones you've just mentioned, I don't remember seeing.
Okay.
Yeah, let's talk afterwards. We can show you the full list of everything we've got there.
This is cool.
Just one more quick. Why Great Salt Lake when we all know that the concentrations are relatively low to other deposits?
Excellent question. So a number of reasons, because we're busy with a variety of other projects, different parts of the world. Utah is one of the top mining friendly jurisdictions in the Western Hemisphere. We won a project here in the US because we're a US-based company. We want to advance critical minerals here in the US. And we've got a lot of infrastructure here as well. What's quite interesting, if you look at the reagents we'll use, we've got sulfuric acid. They'll come from Rio, from the smelter down this way. We've got sodium carbonate that we'll get from the Trona patch out the other way. So Utah's right in the middle of two of the main reagents, good road, rail infrastructure, very strong infrastructure base here, strong skills in the area. So a lot of those variables we had a look at. And we also wanted to prove it on the low lithium concentration brine to prove our technology. So if it can work here, it can work very easily at 2,000 ppm down in Chile.
Of course, we're going to adjust your time, so on those time codes for you. Is this view okay, or do you want it full screen?
Full screen's fine. I don't have any notes.
Okay.
I'm just trying to remember what happened.
Sounds good. Do you want to use the handheld mic or this one?
The handheld's good.
Okay,
Great, so
talk
much.
real loud first, hold it close.
Okay, perfect. All right, well, good morning. For those of you who don't know me, I am Jamie Barnes, the Director of Forestry, Fire, and State Lands. So pleasure to be here with you today. I'm going to walk you through the process of the acquisition of US Mag. So I'll give you a brief history on US Mag. I think most of you know that. We're kind of preaching to the choir here on what went on with this operation. And then walk you through the acquiring of this company through the bankruptcy process the best that I can. Some of this I've tried to block a little out of my head of what went on here. And as you know, this is still kind of very moving still in parts and still in the bankruptcy court. So some of that is still very fluid at this point. So for those of you that may not know, US Mag began extracting magnesium in 1972. Their facility is located in Raleigh on the southwest shore of the Great Salt Lake and is owned by the Renco Group since 1989, but operated under a couple of different names since that time. So the bankruptcy is probably the biggest thing we're going to talk about today. That's the important part of this equation. And this wasn't the first bankruptcy for Renco Group. Magcor went through a bankruptcy in 2002 and then reorganized as US Magnesium, which is what we were dealing with today. So previously, they were the largest producer of primary magnesium in the United States. Many of you have seen presentations where they showed you, aluminum cans, the steering wheels that they made, things like that. And then they started a pilot project for lithium carbonate that began in 2019. So this pilot project aimed to produce battery-grade lithium from cell salts using waste stockpiled from years of the magnesium produced out there on the shores of the Great Salt Lake. And a lot of times we refer to this as the tailings piles. So US Mag had ceased production of magnesium metal over 4 years ago. That was never communicated to the state directly to us from them. No notification given to us. Basically, the way that we found out about that was through royalties not being paid to the state. Us not receiving those royalties. We started receiving calls from reporters asking why they were not producing anymore. We started hearing chatter throughout the community of people being laid off, things like that. The lithium extraction from the waste material halted in 2024. Some of that product remains on-site, off-site, and is unsold. And that's been a topic of concern within the bankruptcy. But it's estimated that there's about 1.2 million tons of waste on-site still today. So what are the division's concerns? So we started really having concerns and looking into that after we started not getting royalties. There's been a long history at this site, but when I took over as director about 2021, we started really closely looking at this operation. And then when production started to cease and we really started looking into the royalty agreement, especially when we weren't receiving royalties, we started to become concerned. Also, we started to learn that Tooele County was owed a great deal of money on property taxes. Tooele County had not been paid property taxes since 2020. They were owed about $6 to $8 million on property taxes. There was an abundance of environmental concerns, as many of you know. We were also approaching an expired MOU for lithium production. There was a dispute on that MOU and when it expired, what the exact purpose of the MOU was with the company. And then we had failed negotiations on voluntary agreements. There was an inability to provide financial viability from the company to the state, and an inability to conform with legislation that had been passed by the legislature for Great Salt Lake. And I'll get into that a little bit deeper as we run through this presentation. And then we were learning of some unauthorized assignments of mineral leases. And what I mean by this is we had other operators out on the site who were producing through US Mag that the division had not consented to. And those consequences were being felt by those operators, but we were not able to resolve those concerns that were going on with the company. We then started to see numerous court filings against US Mag for money that was owed to them, or owed by them to other parties for work that was being done on site and not being paid. There was a lack of environmental consultation. There was a failure to abide by federal regulations and requirements that were happening under the consent decree. And that consent decree comes from the Superfund site and things that were happening with the EPA that I'll get into a little bit later. We then were learning that over the last decade, Renco had provided more than $400 million in financial support to US Mag. Now remember, Renco's the parent company. Through a combination of loans, equity infusions, and credit support to cover operating losses and capital expenditures to the company. So on top of all of that, that were our main concerns with the mineral lease, we also had environmental concerns. US Mag was a large user of industrial lake water, as many of you know. They diverted large amounts of brine into solar evaporation ponds, and despite no longer producing the magnesium metal, they continued to deplete large volumes of water. So in 2009, they were designated as an EPA Superfund site. In 2021, a consent decree with the EPA required US Mag to build a barrier wall. FFSL was not a party to that consent decree. We had concerns over a salt cap that was identified in that consent decree. We were addressing those with EPA. However, US Mag stopped building that barrier wall. One of the actions that I talked about previously being filed for money that was owed to the contractor was for the construction of that barrier wall. It was for millions of dollars, and that wall was no longer being built. That was to prevent the acid pond from leaking into the lake if that were to occur. So if you take all of the environmental concerns and all of the division's concerns, you can basically put those in a bucket. And you can call those the state's lease battle with US Mag. It was a high-stake battle over this foundational lease agreement. This is an agreement that dates back to 1960. It's a sovereign agreement that says they will never pay a royalty higher than anyone else on Great Salt Lake. It's in perpetuity. It's based on them producing. We had questions on that. Were they still producing? Are they holding that lease agreement properly? Is Renco, as the parent company, infusing $400 million over time? Is that US Mag producing? Are they producing in paying quantities? These are all the questions that we had. So in December of 2024, we moved to terminate the lease agreement, alleging multiple breaches, some of what I just spoke of, including unpaid royalties, unauthorized pledging of the lease as collateral, and other environmental allegations. At that time, a receiver was appointed. That receiver took over the company, went in and looked at the books of US Mag, and ultimately that role was downgraded to just an environmental role, where that receiver then just had a close relationship with US Mag, looking at what they were doing environmentally instead of keeping a close eye on their books and having a relationship with that company as financially. And then the division began to work with US Mag again. We tried to work into a settlement. We tried to negotiate a new lease agreement. We tried to negotiate a voluntary agreement on water to fit into the distribution plan of the state engineer that they were required to do based on the new legislation. And we were close. We were getting to the point where we thought we were going to be able to have a new lease agreement, get rid of the lease agreement from the 1960s that wasn't working for the state, and we were going to be able to have something new. The piece that was never able to be answered was that financial viability piece to the state of what was going to be different this time than all the previous times. How was the company going to be financially viable? How were we going to be able to produce in a different way that's healthy to the lake and also a benefit to industry? We couldn't ever get to that piece. So the negotiations collapsed in August of 2025. And unfortunately, we had to go into moving into an administrative hearing. At that time, it unfortunately pushed them into bankruptcy and notifying up that bankruptcy on the state. So US Mag filed for a Chapter 11 reorganization. I won't go into all the details of what the reorganization entailed, but basically they were reorganizing into what they called a new company. But the new company had the same management and the same owners as US Mag. It had a minimal amount of funding contributed by the parent company, who again was Renco, to support operations out on the lake. They had an interim plan to produce sodium chloride for the next 3 years, which was not being produced by them. It was being produced by an unauthorized person on the site. And then they were going to continue to explore lithium. There was concerns with this plan. It was the same plan we had seen for the previous years. So the creditors committee moved to convert the bankruptcy to a Chapter 7. The state joined in that motion. That motion was unsuccessful, and this is a very brief timeline of what was happening. This was over a course of weeks that this was going on. So when that motion was unsuccessful, the court then moved it back to the Chapter 11 and set it for auction. So an auction proceeding in a bankruptcy is basically done to maximize the value of the assets. In this case, Lilac was the stalking horse bid for the auction. That stalking horse sets the floor, the amount, basically, for the auction. And their bid was structured as a credit bid and an assumption of key liabilities. And that was basically to make sure that Wells Fargo, who was a big creditor in this bankruptcy, and Renco were taken care of. That led to concerns for the state overall. One of our biggest concerns was that Lilac was US Mag 2.0. Another concern for us was that federal bankruptcy court exercises supplemental jurisdiction over state law claims. This affects our ability to control our own mineral lease. There was also a potential loss or selling of the water that could happen. Many of you know US Mag has a large amount of water rights. There had been previous disputes over the MOU for lithium. There was still lithium on site that needed to be sold. They wanted to still produce lithium under that MOU, and we had lost control of that as a state. We also had issues with lack of production, as I mentioned before, and the royalty payments. So basically, it was the same old thing, over and over and over again. So we started to execute a plan. We started to think, what do we as the state want? We started to deliberate, how can we become in control of this scenario that we're in now? How do we not let this happen again? We experienced this when MagCorp took over and formed into US Mag. How do we not now become LIMAG and let them control our lease agreement in perpetuity again? So the state decided to form a bid and become a bidder at that auction. We decided to look at what that meant for liability and reclamation concerns. We had to get permission to bid in that auction. That had to come from the legislature and the governor, and we had to find a way to fund that bidding process. We weren't sure what that was. Many of you know what an auction looks like, and I will tell you without going into the details that an auction at a bankruptcy proceeding is far different than an auction when you're bidding on cattle or whatever you may bid on at an auction. It's far different, and it's a little unfair. So you're not bidding on the same assets. We structured our bid very differently to bid on water, facilities, and land, so we could become in control of the process. It was a process of analyzing the risk versus the gain. So in January of 2026, FFSL was awarded the winning bid in the bankruptcy proceedings. The state legislature funded the purchase, and FFSL took control of US Mag's assets in February of 2026 is when we closed on the sale. So the assets that were purchased was 144,790 acre feet of water plus 75,000 acre feet of water out in Newfoundland Basin. We took the buildings without the personal property and 4,500 acres of land, certain easements and right-of-ways, and then we bought back the state's mineral lease option agreement and MOU that were disputed in the bankruptcy case. So what was the goal with this? Well, Utah's home to 50 of the 60 minerals deemed critical, and it's a twofold strategy. It's balancing the health of the lake with critical mineral production. It's oversight and accountability, it's cleanup and reclamation, it's innovation in mineral development, and it was keeping other operators in business. There was other operators that were dependent on having an operator that they were dependent on being a good operator, and that was key to us for them to be able to stay in business. So here's the doers of the situation. Joel Ferry played a huge role in this. As you know, I know you heard from him this week, but getting the funding, taking my call, telling him, here's what I think we should do. Ben, Brian Steed, Mike Begley, our attorney, he's here today, but George Hoffman is outside hired counsel. And back when we started to see that things were going wrong at US Mag, we hired outside counsel outside of the state. We knew that we were going to need a heavy hitter that knew how bankruptcy law worked. And we wouldn't have pulled it off without having him to be able to navigate this. And then the legislature and all of the team at the legislature, natural resources, forestry, fire, and state lands. And there's people that were involved in this that remain anonymous. They don't want to be listed, but it took an army to pull this off. And there's other people at the Attorney General's office, Thomas, Connor, and Trevor. We had 7 attorneys on this case. It was long days. There was a lot going on in the background. But now what? So we have hired 2 former US Mag employees. They have institutional and facility knowledge. We're not plant runners. We don't know how to run a US Mag facility. Ben's learning really quick how to run a facility, but he has a job. There's enough power out there to power the state of Utah. There's a 600-pound, I think 600-pound natural gas line. But that's not what we do. We don't run a plant. So we've hired 2 of their employees. They're doing that. We're working with EPA and DEQ on remediation. We're working with the secured creditors on liquidation of personal assets and lien property. We're working with operators and businesses affected by the bankruptcy. Some of those things that we acquired are the liens that were part of those lawsuits for US Mag. Tooele County's lien, the lien for the barrier wall. We've got to figure out how to settle those liens. And we're also working on innovations related to the water rights and the use of the sites. How do we get a mineral operator in there that can produce in a way that's responsible and good for the environment and within the parameters of how we want to see minerals done here in Utah? And here's some fun facts. The motion to convert the Chapter 7 lasted 3 days in Delaware. This all was going on during, if you remember, the worst snowstorm and ice storm back east that happened this year. It was complicated. It was probably the most canceled travel power out in Delaware. The auction also happened during the start of the legislative session, which was very stressful for the division. We had several canceled hearings due to ice and snowstorms back east. It was an average of about 18 hours a day at the office in a conference room with 7 attorneys and me and Ben, and tensions were high. I think we drank about 9,000 cups of coffee with very little food. And we amended a base budget bill on the floor, which I was told is unheard of in the legislative session, to get the money for this to be done. But we pulled it off, and we'll keep on keeping on. I will answer any questions if you have any.
What's that?
Question.
Okay, I guess my biggest question is the the environmental liability and the environmental situation out there. So, did the state actually buy the environmental liability as well, so is now responsible for the cleanup? And then, if that's the case, what's the is the remedy the same, or is it being kind of renegotiated based on your concerns? And then, what's the timeline and kind of the process on that?
Yeah, so technically we had that environmental liability to start with because of this being on sovereign lands and receiving royalties because of the materials produced. So that was all upfront negotiated, talked about with the state and the legislature when we went into this. But now we are working with DEQ and EPA to determine what that reclamation and remediation on the site looks like. And how that will be taking place. This is all still very new right now because we're still in a place right now where we just got an access agreement with Wells Fargo for them to start collecting their collateral. And that's going to go on probably for the next 9 months to a year. And as far as coming up with a reclamation plan and starting all of that, that's probably in the next year. We'll know what that's going to look like. But as of right now, we haven't started to move on any of that. We've had one initial meeting with EPA that we went back to Denver and met with them.
Where's the money going to come from for that cleanup? Because
right now that hasn't been determined. EPA holds some money right now. They hold about $32 million. And there's other sources where money has been looked at coming from, but no definite identification on funds yet.
So how does that affect the timeline? Is it like 5 years out, 10 years out for the cleanup?
It's not known right now, but we will be doing some messaging on that when we can nail it down and get more definite answers.
Okay, thanks.
Thanks for your leadership on this and great summary. I'm wondering about the status of the dispute over the assets on the site.
Yeah, so Ben can probably answer that better, but it's moving along. We're getting into a better place, but there's still a lot to do on disputed assets and what's going on right now. So.
Thank you for the presentation and for the battle that you fought. It sounds like it was really hairy, and it had really difficult. Do I understand correctly? The hope is that magnesium will again be produced out of that site using lake water?
We don't know. Critical minerals are important to the state of Utah. The goal is to keep the water in the lake and find some type of mineral to be produced eventually, but I don't know what that is right now. There's no plans right now in the works for that. Right now it's to get Wells Fargo's collateral and to get the site cleaned up, but critical minerals are important to us.
Is this on? Okay. Hey, good morning, everybody. I'm Joe Havasi, work for Compass Minerals, and I'm very happy to be with all my friends this morning. Lots of familiar faces. And most of you know Compass Minerals and what we do on the lake, but we're a mineral producer on the lake. And we entered into a voluntary agreement, and just want to talk about what it feels, what it looks like, and how we're doing kind of a year and a half into that. So Compass Minerals owns and operates about 15 operations across North America, Canada, and the UK, and that's what we do. We're mainly a salt producer outside of Ogden. Ogden's unique in that we produce potash there, and that's who we are. So I want to throw a little curveball. Being in mining, safety is paramount. Safety of our employees is paramount. So we start every meeting. We start every meeting with a safety share, usually. So when I had this deck reviewed by our media relations guy, he's like, "You gonna have a safety share?" So going back a year ago, we had a kind of a program in safety, like, what is your why? Like why do you want to come home and be safe? And this is my why. So I want to introduce my wife, Morellis Havasi. She came here to support me. Stand up. Stand up. So it's not something we see kind of in our meetings and what we do, commissions and councils and whatnot, where we talk about family or spouses, but that's my why. So, and she's now a card-carrying member of the Friends of Great Salt Lake. Yeah, I signed her up last night, so. Okay, so I mentioned, it's not just Ogden in Compass Minerals' portfolio. Ogden is our only potash production. Everything else is salt. We have 3 underground mines in the portfolio. In the UK, the only underground salt producing mine, it used to be called Salt Union. But we also have a document and antiquity storage business in the old workings there. To the point where the National Archives stores those types of documents and antiquities in the mine. We have an underground mine in Louisiana on the coast called Cote Blanche, and that produces mainly like highway de-icing salt. And that's mined there and then brought up the Mississippi to everywhere from Minneapolis to Pittsburgh. kind of in the river markets. And then we have the last underground mine, the Goderich mine, which is the biggest, and that produces de-icing salts mainly, and that's distributed throughout the Great Lakes states and provinces. We have a number of solution mines, one in Kansas, Saskatchewan, Nova Scotia, and then kind of distribution depots around the Great Lakes. So just wanted to start out kind of with the footprint of Compass Minerals. The voluntary agreement, and I'll get into the details here, changed our leasehold area. So this is the current sort of leasehold in red, and it's snapped like to kind of the outline of our operations. I'll come back to this a couple times. So what do we produce out of Ogden? I'm focusing on our east ponds, and we produce salt products, highway de-icing salt, agricultural salt, pool water conditioning salts, and those salts come out of this region in the north. And when you look at aerial photographs, I'll help you map it out. When you see red, that's mainly kind of our salt ponds. When you see green, that's indicative of our potash harvest ponds. And then mag chloride is kind of the leftover bittern once sodium and potassium precipitate. So the SOP, we have one product line called potassium, and that's used as a component of fertilizer. And then the mag chloride, about 95% is liquid mag, which is used mainly for like road dedusting, some de-icing component if you desulfate it. But we also have some high-end de-icing products with a lower freeze point that are magnesium commercial de-icing products. We also have ponds that are kind of transitional ponds that aren't harvested. And I think a lot of you know we do a process called mineral return where we run when the Bear River is flowing in the fall and early winter, once irrigation season starts. We'll run that rinsate through these ponds to dissolve some salt and return that back to the lake. Just a high level of how we harvest. We're in the potash regions I mentioned before. You can tell by the green. This is a pond that has it's been debrined, and then we're harvesting the 4 to 6 inches of material that precipitate on an annual basis in an evaporation season. We'll load it onto trucks and bring it to the plant. This is our potassium product. High potassium, all plants need potassium. And we have a niche form of potassium. The commodity form is potassium chloride, which is kind of the global commodity produced, that was mentioned today, Belarus, Russia, Canada are major producers. We also have some KCl at Wendover and Moab. That's the form of potash that's being produced there. Our potash is low in chlorides, high in sulfate. So we can deliver the potassium needed for certain crops without the chlorides. So that's important for all these crops. So from almonds to avocados, berries, citrus, grapes, lettuce, melons, ornamentals, which is a fancy way to say turf grass, but hate to say that here, but it can be used for turf grass. Anything can be used for turf grass, but also peppers, potatoes. So these are high-end crops that the root systems really can't take the chlorides, but potassium is essential. So we provide the mechanism to deliver that potassium. Okay, so let's roll up our sleeves and get into the voluntary agreement. Just kind of completing the thread from the past couple days of good, bad, and ugly. It's been mentioned in a couple of presentations. I think Jamie's presentation had all three, the bad, ugly, and the good. I think it's a good outcome. But we took a different track, and we entered into a groundbreaking voluntary agreement. And in no particular order, things that led up to kind of the situation where this was necessary. Unfortunately, we had consecutive years of drought. not so much the poor snowpacks, but the really dry falls leading into kind of average-ish snowpacks. In the dry upland conditions, it just wicked up everything that was going to come to the lake. And that really affected the recharge of the lake, as everyone knows. Lithium came to bear during this time. So organizing regulatory system for managing lithium. And then U.S. Magnesium's proposal to widen, deepen, and extend their intake canal. That was perceived as a threat, and it probably was like a real threat, because what that would have done is enable the realization of the full water right, even in extremely low lake conditions. So Compass historically and today, and we've committed to it, we kind of roll with the punches. When the lake is low, we pump less. When the lake is higher, then it's available, and we can pump our full water right. But that's really the what was going to happen had that happened in 21, 22. We had excess unused water rights in leasehold. We had 140,000 acres of leasehold. We had 200-some thousand extra acre feet of brine right that had just been, through acquisitions and whatnot over the years and decades that were in the portfolio. And those were rightly perceived as a threat. So we have our footprint now. I showed you what we do in our footprint, but there was a perceived threat of expansion. So if you talk about 100,000 acres, potential incremental expansion, 200,000 acre feet, that could have been deployed, that is papered water. That was a perceived threat. And then we kind of evolved, the state and operators. This is a multiple mineral development area, which is kind of a thing in like petroleum and oil extraction. But we're kind of doing it in the lake too. We've been doing it for decades. Morton, Cargill, Compass Minerals, and U.S. Mag. Like have 4 straws into the lake. And with Lilac's proposal, they're going to be an extra operator on the lake. So establishing a regulatory framework for that, and guardrails, and then guardrails for really a degraded ecosystem that we were experiencing in 22 and 23 with the high salinity and the risk that came along with that. So by that time, fortunately, like people like Christine Rumsey and USGS, UGS really were doing some groundbreaking work at that time, and we had better data, but we really didn't know, sort of how that would play out, and how real conditions would play out. We know now, like at post-berm construction, that was a great fix. That was a great Band-Aid for the moment, and it's really done a great job. So that's playing out now. We didn't know that necessarily. We were seeing that kind of in the models, but just kind of an evolution going on at that point. So let's get into the key elements of the voluntary agreement. Kind of the headline was the relinquishment of 201,000 acre feet of water. It's wet water in a way that it could have been drawn, but kind of an analogy I use is, the 13th ounce of beer in a 12-ounce cup doesn't do anything for you. So you need ponds. So if you're going to relinquish water, then relinquish leasehold, because they kind of go hand in hand with the way we operate. So we relinquished the 201,000 acre feet in addition to the 65,000 acres of leasehold. That would have been a real challenge practically to develop anyways, with the bathymetry kind of in those areas. So we just trimmed our entitlements and holdings to kind of our current footprint, because we had no intention of expanding, to use those resources. So those are the key aspects of it. But in my mind, this progressive brine consumption schedule that's toggled to elevation. I mentioned before, we kind of roll with the punches. When the lake is low, we extract less. When the lake is high, we can do more. So this kind of sets a schedule, really, of how we were operating before, but we've committed to it now. So when the lake's above 4198, the healthy elevation, we can use our full consumptive water right. And I'll just say it, that's 156,000 acre feet is our water right that goes back to 1962, I think. 4195 to 98, 83%. We're still in a pretty decent paradigm, 95 to 98. 93 to 95, 50%. 90 to 93, 30%. And probably the biggest commitment is below 4190 on June 15th, the benchmark date. We're not pumping for the next calendar year. So that's you know, that was a big consideration. Definitely we want to be able to sustain our operations, but in my mind, if the lake is below 4190 on June 15th, we have other problems. That's not going to be a great day if that happens. So there's so many other aspects of the operation that would struggle that you're just we'll stop for the next calendar year and pray that the lake recovers. A couple other things, by committing to the voluntary agreement, kind of wound into House Bill 453 as a severance tax. It was a new severance tax. It hasn't really been hadn't been required to date. So when the lake's below 4198, kind of when we're not at our full efficiency, then we're exempted from that severance tax. When it's above 4198, it's game on. Well, you know, we're subject to the severance tax, but by that time we're playing in the fairway anyway. So, you know, we're doing well. And then, as we all know, like a requirement for improved flow and metering from our intake, which is a really tough thing when you're pumping high volumes of, you know, 1.2 density brine through a pipe. Metering that is really tough. But we're working with water rights and one of their preferred vendors to do that. So how's it going? We've evolved our operating model. So at the risk of like borderline insanity of doing the same thing and expecting something different, we below 4195, we're now not pumping or pumping into our west ponds. So for probably 3 or 4 years leading up to, say late 20-teens through 23, anyone who's heard me talk at salinity advisory committee meetings or other meetings, I'd always sort of complain like, yeah, we're only like down to like 1 or 2 pumps out of 12 in our west ponds. What was happening is the evaporation rate was exceeding our pumping rate. So we're kind of not really getting any throughput through the west ponds. It's all evaporating. Not really all, but a lot of it was. So it's not really worth the effort from an economic standpoint. From a resource standpoint, it's an important resource. So past 2 years, we've temporarily suspended operation on the west ponds. When the lake comes up below, above 4195, again, hopefully soon, we'll resume operation on the west ponds. So we've snapped to an east pond only operation, sub 4195. To that end, we've consumed only 35% over the past 3 years if you would apply the framework for the progressive consumption schedule. You know, we're kind of already in a 30% paradigm right now. We've only consumed, I hate to say only, but we've consumed 35% of that reduced progressive schedule. So we're doing well, kind of snapping to this new east side only paradigm, and we're doing okay. So the reasons why we're doing okay is we have a much stronger command of our mass balance in the east ponds. It really yeah, so we brought on some really great minds in the past several years. So we've sharpened our pencils and have a much stronger understanding of the flow paradigm in our east ponds. So we're really optimizing there. It's been mentioned before, but we do have salt underlying many of our east ponds, and there's like 33% porosity, great transmissivity in that salt mass, so we can draw brine that's an interstitial brine that's in the underlying salt. So we've drawn on that as kind of a bridge resource. And then, as always, we can always buy potassium chloride on the market as a supplement. And we've also evolved to like work with the berm. Mothballing the West Ponds, because we're below 4195, that was kind of the primary concern, you know, back in 22 and 23 when we were considering the first stage berm and the complete berm. Because that impacts the West Ponds. With the new paradigm of temporarily suspending the West Ponds, that's no longer a high concern. So we've really evolved to that. And we haven't talked about it at this meeting, but there's a new salinity rule that's going to be woven into operators' permits, up these permits. So we're going to be working with Division of Water Quality to integrate the salinity into the rule. And I mentioned before we're progressing well on our metering for our intake and returns. So with that, I'll open it up to questions. Okay. Thank you.
So first, I would like to give a big thank you to all the speakers for this morning's session. I learned so much, and those talks were awesome. So how about a round of applause to all of them? Okay, and now we have time for a break and posters. So if you go next door, you can socialize, ask questions, catch our speakers from this morning, and get your questions in if you didn't get a chance. Look at posters and come back here at 10:45.